So because we are going to use some of these equations later on as well, I missed numbering a couple. Let's just assume this is equation 7, but we will need this 8 later on in the material. And after that, we just solved, once we developed the formulation for the settling velocity, we solved this problem for a settling mechanics situation where we calculated the V settling and then found out the Reynolds number of that settling particle. So with that, let's move on. Okay, so the Stokes-Drake formulation that we have found out is true for particles that are much bigger than the main free path in the main fluid. Now let's look at what happens if the particles are very small, smaller than that. Yeah, so let's write down some notes on that and then we are going to derive the formulation if we have to assume particles that are smaller than what we have been using until now. So the Stokes law is valid if we can assume the surrounding fluid to be a continuum which in other words is the d of the particle is much greater than the main free path. So I'm going to represent this main free path with the symbol lambda. Let's call it lambda Fp. Now, as I did mention in the previous session, that this lambda is around 0.07 micrometer for air. So for air at room temperature, and 1 atmospheric pressure, this lambda Fp is around 0.067 micrometer. Now, is this a good enough assumption? Well, as I said, it depends on the problem that you are trying to look at and the particle sizes that will be relevant for that problem. So for example, for drug delivery, if you are applying some kind of formulation with the particle sizes that are geared towards the smaller end, you might have to be careful about using these assumptions. Similarly, for infection transmission, if you are looking at particles that are sub-micron, there could be some that are suspended in air, you need to be careful about that. So, while pharmaceutical particles or aerosols typically start from around 0.5 micron, the inhaled pathogens, some inhaled pathogens could be much smaller than that as well. And closer to even this lambda Fp. Now, what happens if we do need to consider those so-called very small particles? So let's check what kind of correction we will need in our formulation if the particle sizes get smaller than what we have been using until now. So the drag force on very small particles. So we need some correction factor. It is called the Cunningham slip correction factor. So with the Cunningham slip correction factor, CC, we have a revision. Oh, sorry. Yeah, so let's call that CC. So that CD, the drag coefficient, is now 1 over CC times 24 over RE, what it was before. So therefore, the drag force just gets this extra factor CC in whatever we had before. And of course, RE is still much smaller than 1. And following the same line of calculations as we did before, we can figure out that the V settling in this case would be CC times rho particle d squared G over 18 mu. So this is the correction to equation 4 on our lecture notes. Now there should be a way to calculate what is this Cunningham slip correction factor, and it is a function of the mean free path. So the approximate formula for the correction factor is CC is 1 plus 2.52 lambda FP divided by D. Now if you apply the length, the actual value for the lambda over here for the typical particle sizes that we are looking at. So for example, if we use for D greater than 0.1 micron, if you apply lambda to be 0.067, you will see that this becomes very close to 1. And we're going to use some numbers in the problems that we're going to solve next for this. But in general, as you can see, this because of this component over here, CC is always going to be greater than 1. As a result, the V settling width for small particles is the velocity is larger than the settling velocity for the particles that are slightly bigger, and the other way around, the drag force here is smaller than what we had before. Okay, so with this, let's solve another problem. And do we have more calculators in the room? Or okay. So from now, for the examples, I would probably go a little slower so that you guys have time to do the calculations. Okay, so evaluate the settling velocity in air for a 0.5 micrometer diameter spherical droplet of nebulized Ventolin respiratory solution. So just for our knowledge sake, let me write down what this compound formulation is. So this is 2.5 milligram per ml of salbutamol sulfate and 9 milligram per ml of sodium chloride. in water. So calculate the settling velocity in air for this sized particle, both with and without this Cunningham slip correction factor. Okay, so in terms of the given parameters that we would need to know, the viscosity of air is, as before, 1.8 times 10 to the power of minus 5. So let's start with the solution. And we have just derived the formulation for the settling velocity. So V settle is Cc rho particle d squared G over 18 mu. Now what we have not been told is maybe we are given all the information. So we can assume that this is, okay, do we know all the information here to apply this formulation? Cc is something that we can find out using lambda and the d, right? The lambda, as I told you, although I have not written down in the problem statement, we know that value for air. The d is known, the mu is known. Do we know the density of the particle here? We don't. So we have to assume something. So based on the compound, and this might be something that would be unknown to us engineers, but we can assume based on the nature of the compound, this is very close to a water-like solution. So let me write that down. So presuming that the pharmaceutical agent and the salt have negligible effect on the solution density, we can hence apply the different numbers into the formulation. So Cc is something that we are trying to find, evaluation settling velocity. Okay, let's Cc we don't know yet, so let's keep it like that. The rho particle is 1000 kg per cubic meter. The diameter is 0.5 micron, so 0.5 times 10 to the power of minus 6 meter squared times G divided by 18, 1.8 times 10 to the power of minus 5 kg meter second. So CCI left it like that because we have to do it both way, with and without the Cunningham slip correction factor. So if we don't consider the CC, so therefore without CC, give me this number. What I have is 7.57 times 10 to the power minus 6, right? Yeah. So this is meters per second, and with cc, so the cc correction here is 1 plus 2.52 times 0.067 micrometer divided by d, which is 0.5 micrometer. So how much is this? 1.01. Is it the cc or the V-settling? V-settling. Okay, you are probably right because I have a different unit. So this is 1.338, I believe. Therefore, the V-settling is this correction factor 1.338 times the settling velocity that you have found before without the correction factor. So 7.57 times 10 to the power of minus 6 meters per second. So what I have here is, converting the units, 0.010 millimeters per second. Is that what you found? Okay. So if you just compare what changed between the two, you'll see that the settling velocity, if you do consider the effect of the slip effect or not, the settling velocity just changed by quite a bit. So the settling velocity increases by, it is 0.01 minus 0.00757. If I write the first velocity in millimeters per second, so it would be 0.00757 millimeters per second. So which, if you calculate, will be around 32%. So it changes by quite a bit just by doing the slip. Now, what is the driving factor over here? Because if you think about the structure of the slip correction, you cannot do anything with this 2.52 or this 0.067, that's fixed for air. So that means that if you have smaller particles, you need to be careful about whether you want to include that correction or not, and you probably need to include that correction. And hence, for very small particles, we do need to include this into our mathematics. Okay, so until now, including this problem, we have been talking about how in stationary air particles would settle. Now, what happens if the particle is actually so fast that it is moving with respect to the fluid and there is a strong component of inertia in its motion? And that inertia, think about the particles. Let's again assume a drug delivery application for it. So, as we spread the particles, the initial speed of the particles is quite high. Anyone can guess what the initial speed of these particulates are as they come out of the spray nozzle? It's on the scale of 10 meters per second. Very high. So, based on the size of the particles, their inertia is quite strong. And many of them, they actually land so in the very outer part of the nose. If you think about this 3D print, many of these particles, they would end up right over here. And then they move with the mucociliary stream further down the tract. So the initial impaction, which is what is happening then, is quite important, especially for drug delivery applications. So let's take a look at that. Yes. So we did not, we took the density as water. We did not take the surrounding medium as air. So over here, so this is where we took the density, right? We approximated it to be water. The surrounding fluid is air, so we did not take it as same as the surrounding fluid. So these are little water particles that are moving. So think of a nasal spray solution, you are applying it inside your nose as you are breathing. But your question could also be, is it realistic to assume it to be a water-like solution? So that's a good question because this has a chemical compound, it has sodium chloride salt. So it is going to be very close to water. It probably could be 1050, 1020. What we are doing in our lab right now, there is a study being run where we are actually varying the density by quite a bit. So we start from 1000, we go on to 1500 and see what we are going to do. But if you look at the different commercial spray products that are out there, in their modeling studies, they are again that it's water. Okay, so now let's.
Regarding the nasal spray,
Yeah.
which one is like, is there a higher settling velocity or more, or like what is the motivation of changing the fluid density? You were saying like 1000 to 1500 you are doing.
The settling velocity is important depending on how the nasal spray is hit. Because if you are directing the nasal spray, so is there a shock here? You can just.
They have this top box, the white one.
Just
That
give me a
called
second.
maybe the black pain also you can. Marker pain is there.
Okay. Okay. So this is just a quick diagram. So basically, if this is the node, and if you are holding the spray bottle like this, so these particles they go up. Now let's assume that the particle comes to the velocity dies down and it's trying to settle in stationary rate. Then if it is trying to settle, for example, over here, like this, if this is a target site that you really intend it to be, then it is useful, right? But if it is not the target site, you want the particle to reach further back in, then this settling is not useful. So whether the settling mechanics is useful for a non-delivery application, that depends on what your target sites are. And as we are going to see in a couple of days, the target tissue sites are preferred for different clinical conditions. Yes.
I have never used this kind of thing, but is there for a particular setting, can there be different targets, or is this mechanism usually targets the same place?
There could be different targets. So for example, let me show you some pictures over here. So this is something that we are going to see later on in this module. So this is a respiratory area that is built for CT scans. This blue region over here, it's called the nasopharynx. It is where the two sides of the nose merge together. So when you get a cold, for example, that sore throat sensation that you get is basically over there. Because that is the trigger site of many infections. So that is one particular target site for some of the pathogens. But is it so for others? Not really. So for example, there could be a pathogen that mostly infects this anterior part. Or for example, even pox family viruses, because monkeypox is out there, so we are working on that as well. They actually start out further downwind. Now what this nasal sprays can do is to send drugs to certain sites. Now your question was whether all nasal sprays send the drugs to the same region, right? So what was done in this paper is, so over here we are placing the nasal spray in two different angles. So in this one we are trying to put the spray axis such that it actually cuts through that target site. This is where we want to send the drugs because that's what the infection is. Well, this one, this is according to the instructions that come in the packet of the product. We saw that there is a significant difference in terms
They
of.
mentioned you have to spray like this or like this.
So you can revise the protocol. So by revising the protocol, you can actually change how much drug would reach the target site by quite a bit. So for example, this plot over here, those red lines, are for the revised protocol. The blue lines, you cannot see the color here, but the blue lines are for the old protocol. It is also a function of the geometry of the area. So whether you get a direct line of sight access to the target site, that's a function of the geometry. But typically you do improve a lot just by a different way of working with this. Anyway, so these are some of the papers that we should be studying at some point during this week. Okay, so on to inertial impaction. So let's try to develop the equations for that. So motion of particles relative to the fluid owing to particle inertia. So as I think I already mentioned, that sedimentation is an important mechanism for regional deposition. The initial impaction has to be studied as well based on certain parameters. So let me write down some comments before I try to develop the mathematics here. So besides sedimentation, which in our application would be always under gravity, another important mechanism that can cause inhaled particles to move relative to the ambient fluid and deposit on the walls is particle inertia. And sometimes it works to our benefit, sometimes it doesn't. It would work to our benefit if the target site is such that the initial motion of the particle would direct it over there. But otherwise, we have to think about other ways to send the particles. If it is a drug delivery application, if it's an infection mechanism application, then the questions are different. We need to know the particle inertia properties to figure out how much of the infectious load would reach the infection prone sites along the airway. Either way, we need to understand how the inertia impacts the trajectories of the particles inside the airway. So, to assess whether a particle will deposit by impaction, we again would go back to the same equation. So m dv dt is mg plus f drag. Now, over here, what can we ignore? So, first of all, now that we are using this equation where we are going to isolate just on the inertial interaction, we're going to get rid of the second term on the right hand side. So, we're going to get rid of the gravity effect. We're going to use the F drag formulations that we had before and see what we can derive from here. What we are going to see is there is a specific time scale of particle relaxation time that we can use to characterize the mechanics, and that is something that is going to help us to non-dimensionalize all these equations as well. So let's try to do that. So this is to assess the inertial dominance. So dv dt is g plus, we are going to use the f drag. So this comes from the equation that I have marked as equation 4 in our notes. So from equation 4, we get minus 3 pi mu d over cc over v minus v fluid divided by m. So let's try to simplify this a little bit. So dv dt is equal to g minus 3 pi mu d v minus v fluid by cc by, this is 4 by 3 pi d cube over 8 rho particle. So let's now cancel the different terms that we can cancel. So sorry, this is cc. So this becomes 18, the pi's get cancelled, the d, one of the d's would get cancelled as well, so this makes it d square. So the 18 factor comes from here, so 18 mu divided by d square rho particle, rho p, rho particle, and then the cc correction factor is here. This multiplied by v minus v fluid. Tell me if I miss anything here. So 18 mu divided by d square rho particle cc v minus v fluid. Okay, what is this particular term? So this has a special name, or the inverse of it has a special name. So this I can write as dv dt is g minus 1 over tau v minus v fluid. So this tau over here, if we check the dimensions, it has the scale of time, and it's called the particle relaxation time, which is going to come back again in our material source. So let's name this particular equation. So let's call it equation 9. So with tau being equal to rho particle d square cc over 18 mu. So this is this parameter tau is the particle relaxation time. And let's call this equation 10. And this tau would be useful, as I said, when we normalize these equations. Any question, Abdullah?
What is the critical meaning of this particular relaxation time?
What is what?
Critical meaning.
Physical meaning of the particle relaxation time. Uh, can you tell me based on this equation what you think would be the physical meaning of this? If you don't have the g component, and if it is stationary fluid, so it becomes v over tau, right? So dv dt, so that gives a direct sense of what the particle velocity would be like, the time scale for that velocity to compute it, if it is a stationary air and if it is falling through that. So that is one way to think about the physical nature, but you can think about it in terms of other non-dimensional numbers as well. So I'll come to that in a moment. But this term by itself, it is very similar to Stokes number as well. So Stokes number is a non-dimensional particle relaxation time in certain sense. So you just need to add some terms, cofactors to this term, and it will become the Stokes number. So there is that way to describe it as well. Or even, as I said, you can use this equation to describe what the physical nature is.
So isn't the time
like particle takes to catch up the fluid velocity?
That is one way to think about it as well. So if you put a particle which is initially at rest in a moving fluid, the time it takes to reach that velocity. Or if the particle, if the fluid is at rest and the particle is moving, the time it takes to come back to that state of the fluid. So both ways it would work if there is a difference in velocities. Okay, so from here we are going to use this tau, but let's define a few other mean terms that we can use to non-dimensionalize these equations. So let us now, so we are going to use this equation 9 for the non-dimensionalization. So let us non-dimensionalize equation 9 using u naught. So u naught, you can think of it as a velocity in the fluid medium where you are trying to study the particle transport. So if you think about particles moving through the airway, if you are just looking at the upper respiratory tract deposition, it is a u naught, which is true for the upper airway. But rather, if you are trying to look at what is going on further downwind in the bronchial region, it could be a velocity that is in the near the alveolar sac. So it is dependent on the problem that you are trying to study. So u naught is a typical velocity in the fluid flow. So u naught is a typical velocity in the fluid field along the respiratory pathway. So it could be, as I said, depending on the problem, at an appropriate region along the respiratory tract. We need a d. It is a typical dimension of the geometry along the respiratory tract again. Now, the geometry of a respiratory tract is quite interesting. It covers quite a few orders of magnitude. So it starts from on the scale of centimeters and reaches near the alveoli, which is approximately around 100 micron on an average. So it starts from centimeters and reaches to microns. So as a result, if you think about this d, the d itself can vary a lot based on which region of the airspace you are trying to study the transport in. But whatever the typical value is what we are going to use in the problem. So let's use this u naught and d to on the equation 9 that we have derived in the previous page. So we will couple u naught and d to go to a characteristic time scale. D over u naught. So let's put that into equation 1. Therefore, in equation 9. So equation 9 is this. So if we non-dimensionalize this v, so v divided by u naught by dt divided by d over u naught. And to adjust, we put u naught for the other u naught here and d over u naught. This is equal to g minus the v bar is non-dimensionalized with respect to u naught, and the v fluid is also non-dimensionalized with respect to using u naught. So as a result, this becomes u naught for the correction and then a tau. So this is what we have. So let's now use this particular form. So from here, let us now introduce some new terms instead of using this particular formalism for the velocities and the times. So subsequently, let us introduce the following non-dimensional variables. So V bar prime is V bar over U naught. Then we need a V bar fluid, which is V bar fluid over U naught. We need, if we want to use the V relative formulation, we need that as well. So V rel prime is V bar prime minus V prime fluid. What else do we need? We need the T prime as well, which is T prime is T divided by D over U naught. Do we need anything else? We need the G as well. So let's assume G bar hat instead of prime to be G bar over G. And let's call the equation before this as equation 11 on my lecture notes. For the chronology of the equations, do follow the lecture notes that I've posted. I might be missing some of the equation numbers as I write here. Okay, so let's now plant all these dimensionless variables into equation 11. So equation,
The last variable on what is this? This is the G.
the G.
So this is non-dimensionalized to the magnitude of G or
With the magnitude.
so you need vector.
Right. That's why you're using the hat. Okay, so we are calling this as equation 11. So this equation 11 using this terms that I just introduced would reduce to would now reduce to so we have so the first cofactor is by itself u naught square over d. But this now becomes dv bar prime over dt prime. Then the g becomes g times g bar hat minus u naught over tau by multiplied by v prime minus v fluid prime. So yeah, sorry. So this is what equation 11 is by adjusting by simplifying the cofactors and putting in the dimensional variables. Let's now try to simplify this a little bit more. So tau u naught over d. So I'm going to use the definition for tau that we have used. So I'm putting the tau on the other side, and then eventually I'm going to use the actual formulation for tau to move forward. But for now, tau u naught times d is dv bar prime dt is tau times g over u naught times g bar prime minus this particular term over here becomes v relative. So let's block this equation out. Let's call this equation 12. What is this coefficient? What is the second most well-known non-dimensional number in fluid mechanics? Not Reynolds number, it's the Stokes number, right? So this coefficient is equivalent to what we know as the Stokes number. So I'm going to write Stokes number as STK to distinguish it from Thrall number. So STK is tau u naught over d. Let's now plan in the expansion for the particle relaxation time tau that we have found before. So STK is rho p d square cc over 18 mu for the tau part times u naught over d, which is what I was trying to refer to as this is tau and this is u naught over d is 1 over t, t inverse time scale, right? So basically you can think of the Stokes number as dimensionless version of the particle relaxation time as well. So STK is u naught rho p d square cc over 18 mu d. Yeah, sorry. So this, let's call it equation 13. Now, what else can we do with this? We have been using in equation 12, if you go back, we have still not left out G, although we are trying to just study the inertial interaction. So we can do something about it, and that can help us isolate more on what is referred to as or what happens with inertially dominated mechanics. So let's do that. But before that, let's try to think a little bit about this particular formalism as well, what else we can do, because as you can see by now, many of these right-hand sides for different terms, they look very similar. If you go back to the equations that we have been deriving since morning. So let's dwell a little bit more on this before we move on to the exclusively inertial conservation of the mechanics. Was there a question? Okay. So now recall that the V settling that we had derived before lunch was Cc rho p d square g over 18 mu, right? So what we can do here is think about this particular part. So rho p d square over 18 mu. What is that? That is rho p d square over 18 mu. We have just derived that. It is the tau, correct? So this part itself is tau. And what else do we have? So Cc times tau Cc times tau times g. Let's quickly look at, is that indeed the tau? Can you look at your notes? Yeah. So tau is this. So tau is rho p d squared cc over 18 mu. So tau does have the CC. So we have to adjust for that. So if this is this, then let's write it as V settling is CC. We are going to bring the tau part here, the squared CC by 18 mu. But for that additional CC that we bring in for the tau, we have to add a correction 1 over CC times G. And there should be a mu in the denominator. Yeah. So now I can call this part as tau, but this CC and this CC, they get cancelled out. So what we have here is V settling is this tau times the G. Correct me if I'm wrong. So V settling is tau times G. So let's try to use this in the formulation because of what? Because we still have this tau G over here. So we can possibly use it over there. So therefore, in this equation 12, let's try to apply this. So in equation 12, we have tau u naught over d times dv prime dt. This tau g is v settling, we just found out. So tau g is v settling over u naught times g bar hat minus v relative bar. Let's write this as Stokes number, which is what we already found out. So this is Stokes number times dv prime dt is v settling over u naught g bar prime minus v well prime. So let's block this equation out again. Let's call it equation 14. So this is finally the non-dimensionalized version of the equation of motion of spherical particles moving through a fluid. Well, we have considered all the terms. We have not yet left out the g term, the v relative, the inertial term is still there, and we have everything else that we need in the more generic version. So this is the non-dimensionalized version of the equation of motion for a spherical particle. Okay, so now that we have this, we can think about the orders of magnitude of each of these terms based on the question that you might try to address. So let's think about the first case being if the Stokes number STK is approaching 0, what happens then? So if it is approaching 0, you have the left hand side 0, that's fine. So if STK is approaching 0, the left hand side in equation 14 is 0 as well. But what happens to the right hand side terms? So on the right hand side you have V settling. So on right hand side you have V settling, which is, if we again use the formulation that we have derived before, so slip correction factor times rho p d square g over 18 mu, right? We can rearrange this right hand side of the V settling to see how it depends on the Stokes number. So let's do that. So if I write this as rho p d square cc over 18 mu times u naught over d times d over u naught times g. So basically, we have brought in this word. The rest is same as what we had, the g and the u. So this becomes the Stokes number now times d over u naught times g. So if that is the Stokes number, then that implies that if Stokes number is going to 0, this is going to 0 as well. So therefore, the right hand side is in equation 14. This is 0. You just are left with the v relative. So right hand side, or the term 1 on the right hand side. So term 1 on right hand side of equation 14 is approaching 0. That being the case, therefore v relative is v relative is 0. What does it tell us? What is when v relative is 0? That means that the velocity of the particle and the velocity of the fluid they are same. So this implies that the particle trajectories are the fluid streamlines. So physically, when we try to think about this, what does this mean? If we have a particle with a very low Stokes number, they're going to follow the fluid streamlines. The fluid streamlines on which they were initially embedded. So, and what are the particles with a very low Reynolds number? So the Stokes number, a very low Stokes number. The Stokes number is dependent on d square. So it's proportional to the square of the diameter. So the smaller the particles are, Stokes number is going to get smaller even faster. So for those particles that are very small, typically smaller than 5 microns, because that's where the distinction is. Those are aerosols. They follow the fluid streamlines on which they are embedded when we are inhaling. Think about drug particles, think about particles with pathogens. They tend to follow the streamlines and go into our tail plants. While the bigger particles, they don't have this particular setup in its patterns. The V relative cannot be zero for the bigger particles with a stronger inertia. They cannot follow the streamlines. And as a result, they deposit much earlier. So whatever streamline they might be embedded in, they soon fall out of that streamline and deposit locally somewhere in the anterior part of the body. So the Stokes number hence helps us to understand where the particle might land in general. Does it make sense? Any question?
So here the relaxation time is zero.
Right, right, yeah. I mean, if you think about the Stokes number as another version of relaxation time, non-dimensional version of relaxation time, Stokes number will be zero is relaxation time. So that's another way to think about it. Huh? Oh.
So it's almost 1 hour. You can engage in questions regarding this. Then we can start the next session. So any more questions related to this, you can ask now.
Any other questions?
In the drop also, like example, if the drop is not exactly
Second.
if the drops are not typically water, like some polymer or something else, so the one thing changes the density. So that brings the change in the Stokes also. So this goes to also.
Yeah, so basically then you don't only have to worry about the size, you have to worry about the rho p as well in that term.
Yeah, which is how can we can relate it to the actual drugs. They are not just
Yeah, so basically there is a problem that I have to solve. So when you are trying to evaluate the Stokes number, yes, the D is important. That's the mechanics work. The material work comes into the mu, not the mu, but the rho p. The mu is the mu of the surrounding fluid, so that is not the material property of the rod. The rho p is important, and if you have some kind of polymer, so that rho p is different. Now, whether the rho p can balance the squared chrome of the d is a good question, right? So if it is like a, say a point, say a, even a 2 micron particle or a 1 micron particle, because of that small d, there is always that huge impact on the Stokes number getting much smaller. Now whether the rho p not being 1000 kg per cubic meter but rather being 1100 kg per cubic meter, whether that is enough to balance that effect is a good question.
The consideration that you showed are the typical consideration that there it won't be that much of a difference.
What do you mean by concentration?
Means in your example that you showed,
The compound concentration. Yes. That's what
in those conditions it will be almost just like the
close to water.
Very close. Not even more than 2%.
And that problem statement, if you read it, it said that this much in water. Now, if you start out with a different chemical altogether, can you still assume water like? It depends on the chemical, right?
If the base is different,
If the base is different, then
maybe if it's in alcohol, then maybe.
yeah. What's the timeline like?
So, like almost 1 hour. We started at 4:05.
Okay, so what we have here is, let me just quickly go through because I don't want to break at an odd time. What we have next is actually a problem we're going to solve. So yeah, so we are going to use these formulations, but it's a new problem, so we can stop there. I do plan to spend some time tonight to read the paper that I was telling you guys about, because I think based on my progress, you should be ready to at least read through the paper quickly tonight. Okay. Yeah, did you
You can
share?
send me, I will just, yeah, I will send it.
So it's on the clouds folder.
So
So
just tell me the name of the
I'll write the name of the paper there. Okay. So how long are we taking up?
So what is the time now? This is
Okay.
official time is 3:30. You can start at 3:30 and then if needed we can extend
Yeah.
like little more than 1 hour.
Right.